When it comes to the plasma membrane, it is literally the key. This outer boundary of this individual cell is the key to having complex structures. It is the key to how stuff gets into a cell. Hell, it's the key to how stuff gets out of the cell, all right? So this little boundary is more than just a little boundary. There's a lot that goes into it, and we're going to try to hopefully present some of that fun stuff here. If I can find my mouse. I'm just having a hell of a day. Okay, so it's kind of what we're looking at here. We're going to go into the plasma structure, the plasma membrane structure. What is it? What's in it? What's on it? Ways we get stuff in and out of the cell, okay? Through passive transport, through active transport. And spoiler alert, that active or passive is based on how much money we got to spend, how much energy we got to spend, how much ATP do we got to spend to get stuff in and out of a cell. And then we'll look at some modifications of the cell surface, all right? Because, I mean, we have a cell here, but the human body, and that's how I'm approaching this thing, is so dynamic, all right? You have a cell that sits here, but we have a number of cells that stick together, all right? And cells are a boundary between the fluid on the outside and the fluid on the inside. Well, hell, it's more than fluid, all right? There's a lot of stuff that's found in that fluid. Cells, fibers. Some tissues have a lot of fibers. Some don't have very much at all, like blood. Blood doesn't have really any fibers unless you cut yourself. Then fibers come out of solution and we form the blood clot. Bone has a lot of fibers and it's solid. Your tendons and ligaments, it's a lot of fibers and not a lot of fluid. So they provide a heck of a lot of strength. So there's a lot of variation that occurs outside of an individual cell, and that's what we're going to try to hint upon here in that last part of the class with modification of the cell surface, all right? So here we go. We're going to talk about the plasma membrane and dive on in here, all right? Plasma membrane or cell membrane, okay? There are multiple different ways that you can say it. I use them interchangeably, okay? I use them interchangeably. Okay. And its primary claim to fame, right? Keeps the internal in, keeps the external out, okay? So it's a barrier. Barrier. Okay? It is a barrier. That is its ultimate function, right? It is the gatekeeper. It is the barrier. It is the gatekeeper. It gets to decide who can come in and who can't come in. Okay? It can decide what type of chemical reactions can occur within it. Because it's these chemical reactions that are going to drive the ability to make ATP. We refer to this model as the fluid mosaic model, okay? That's what we call this structure of the plasma membrane. If I just go ahead a few slides here, here is the fluid mosaic model, okay? These are all the components that we see within this plasma membrane, and it's the stuff that's, you know, highlighted in color here, okay? Plasma membrane. So when we talk about this fluid mosaic model, we're talking about all these fancy pants components. So let's go back and talk about these fancy pants components, all right? The plasma membrane ultimately is a phospholipid bilayer, okay? Bi means two. Okay. Layer means layer. So we have two layers of phospholipids, a special kind of fat, special kind of lipid. Okay. Special lipid. Okay. And we get a bunch of these strung together here. There you go. Okay. You catch on. You catch my drift here, right? Of course you do. Okay. We have the external surface lined with hydrophilic polar heads. Hydro means water. Philic means love. So these are always going to orientate towards the water, whether that's outside of the cell or whether that's inside the cell. Okay. Sorry. Okay. So that's what that means. All right. So they're always going to be orientated. So that way, if we bring stuff in or we get rid of stuff out of the cell, this phospholipid bilayer is always going to orientate those heads towards the water. It ensures that we don't destroy the cell. Okay, because if I can't maintain the integrity of my plasma membrane, the barrier doesn't work. All that fluid comes into the cell and destroyed. Here in the center, and I should use a different color. Let's use a different color. Okay, red. Okay. In the center here, I have my hydrophobic fatty acid tails. Remember, phospholipid, a phosphate head, and lipid tails. So here those are. These are hydrophobic. They fear water. They don't like water. They don't interact with water. Excuse me. Okay. They don't like water. So this phospholipid bilayer always orientates in this fashion. Okay? Always orientates in this fashion. Again, to ensure that this barrier is maintained. Because again, that barrier is key, guys. If I destroy that barrier, all of the things that are inside can get out and all the things that are outside can get in. And that negates a barrier function. When we look at this phospholipid bilayer, this plasma membrane, you will notice three kind of basic components, and they're all expounded upon. Okay, they'll be expounded upon a little bit here as we go through. But we have three major components. Again, the lipid component that we just saw, all right, the phospholipid bilayer, that's the big one. Okay, and as you can see there, it's, okay, you can see it kind of undulates and moves. Okay, so it's pretty dynamic. Pretty dynamic, all right. We have proteins embedded throughout this phospholipid bilayer, okay? And if you remember that video from way back that we showed at the end of the last lecture, we saw those little proteins, they can float around like tiny little icebergs, okay? Some of them can float around the periphery, and they're only found on one side. I don't like that. Found on one side. Because you're going to have peripheral proteins found on one side, and you can have some on the inside as well. So peripheral proteins are going to be proteins that are found only on one side of that plasma membrane. Okay? Only found on one side. Okay? There can be some up here. Okay? Only found on one side. All right. So when they're found on one side, we refer to those things as peripheral proteins. There are some proteins that span the entire width of this phospholipid bilayer. When they span this entire width of this phospholipid bilayer, we call those integral because they are integrated into the plasma membrane. So I've got fat, phospholipid bilayer, type of fat, type of lipid. I have proteins. Proteins can be found on one side, peripheral, or found spanning the entire width of this plasma membrane, integral. We also have cholesterol. Okay, we also have cholesterol. And cholesterol is bad, right? That's what you've all been told. Well, you've been fed a bucket of lies. Cholesterol is actually pretty good. Now, there's good cholesterol and there's bad cholesterol. Okay, if you consume nothing but the bad cholesterol, Yes, cholesterol is quite awful for you and you'll be dead. Okay. But cholesterol is good. Cholesterol is the precursors for vitamin D, which they're finding that if you have a pretty significant deficiency of vitamin D, you're generally the one that gets COVID. Also, obesity has a role into it, and diabetes, and there's a lot of comorbidities into it, but vitamin D is one of those. We get vitamin D from sun hitting our skin and turning that cholesterol in our skin to vitamin D3. You also consume vitamin D as well, all right? But cholesterol is a precursor for that. Cholesterol is a precursor for hormones, estrogens, testosterone, okay? So it's going to make the sex hormones. So for women, it's a pretty important thing. It is for guys too, okay? But if women drop down their hormone levels, I mean, that can really affect their ability to get pregnant. That can affect whether or not they menstruate. And if they don't menstruate, then a long time without menstruation generally means low estrogen, and that usually means poor bone health. So cholesterol is something that, you don't want to get rid of completely because it is so important. In terms of the plasma membrane, it creates a much more fluid type of membrane. Okay? You want your membrane to be fluid, okay? Which means you just want it to be loosey-goosey, right? Okay? You want it to be able to move and bend, right? As soon as I bend my arm here, I'm bending that blood vessel, okay? And when I bend that blood vessel, that tightens the turn there that red blood cells got to make to get around that little bend there. So I want my cells to be able to bend and get around stuff, okay? And that fluidity is a product of cholesterol, okay? So it gives them some fluidity. Again, I don't want my membranes stiff and hard. That's atherosclerosis, hardening of the arteries, arteriosclerosis, okay? If cholesterol builds up in the walls of the blood vessel, that can really stiffen the blood vessels up, makes them less pliable. So now they're stiff and hard, so they don't pulse as much. So cholesterol and fluidity go hand in hand with one another, and they're so important into what a plasma membrane is. Fluid. Another major thing, and they probably should have done 4 things, to be honest, but I see what they're doing here, okay? Because they're attaching this to a protein and a lipid, of which we already talked about, phospholipids, cholesterol, proteins. So I get why they didn't put this in here, but really in the grand scheme of things, guys, there's really 4 major components found in the plasma membrane: the phospholipid bilayer, cholesterol, proteins, and this one here, carbohydrate chains. Carbohydrate chains are important because they tell you that it's you and not somebody else. We have around the outside of all of our cells inside my body, there is this coat that basically says that is me, and my body doesn't attack it. Now, a foreign invader comes in, it's going to have a different coat. It's going to have a different carbohydrate chain around the outside. So when that different coat comes in, those different chains come in, that allows the body to say, hey, that dude shouldn't be here. All right, let's go see who it is, and then we're going to get rid of him. Okay. That is what the carbohydrate chains do. All right. We can have carbohydrate chains attached to proteins. So glycoproteins, glyco is glycogen, which is a carb. Okay. So glyco is carb. So you can have this carbohydrate chain attached to proteins, and you can have this carbohydrate chain attached to lipids, okay? There is some degree of slight variation in the function of these, but still, ultimately, they're both in the business of cellular identification, okay? Whether it's to see a foreign invader and mount an immune response, or to make sure that that sugar coat is as close to your sugar coat as possible so you can get tissue from somebody else, okay, if you need a transplant for some reason, or a blood transfusion, okay? The more specific we can get those outside chains to be comparable to one another, the greater the likelihood of success of a transplant or a blood transfusion. So there's your fluid mosaic model. Phospholipid bilayer, cholesterol to give fluidity, proteins embedded to ultimately do a buttload of crap, which we're going to see here in a second, and the number of things that are coming off of it, glycolipids, glycoproteins, and all of these are there to basically identify, hey, it's me, or hey, that's a foreign invader, let's go get them. All right. These proteins are super duper dynamic. Okay. Cholesterol has its claim to fame, fluidity, super duper important. Okay. Phospholipid bilayer, it's important. It helps to maintain the integrity of this boundary. Okay. Helps to keep the out and the in. But it's these proteins that do a number of things for a cell. And over the next couple of slides, we go over those. Okay. The first function, they function as a channel protein. Well, I mean, you can see it right here. There's a channel right there embedded within this integral protein. Okay. So we can bring in specific things from the outside, get it into the cell, as well as from the inside and get it the heck out. Okay. So these are channels. So they allow the passage of molecules through those membranes. Great. This allows us for entrance and exit of stuff. Some things can dissolve through the plasma membrane, okay? And when we talk about how we get stuff in through passive membrane transport, we'll talk about diffusion. They just diffuse right across the plasma membrane. They're lipid soluble. Some things aren't lipid soluble, okay? They're water soluble. So those hydrophobic tails, they're gonna be, I don't want water here, I'm afraid. They're gonna repel it, okay? So sometimes proteins act as carriers where they'll grab this guy and escort him across the plasma membrane. So they're going to assist, and we'll talk about that in active and passive transport. Well, we just talked about recognizing, okay? I mean, we just saw that, so helps the body recognize. It is a receptor, okay? Whenever you see receptor, you think specificity, okay? This allows the cell to respond to specific molecules, all right? You have receptors for bringing across cholesterol. If you don't have those receptors, you have elevated cholesterol in your blood, okay? And it's a genetic disorder. You have receptors for specific neurotransmitters, chemical messengers inside the nervous system, okay? Where they only dock a specific neurotransmitter, acetylcholine, okay? Serotonin, all right? These are examples of some neurotransmitters, all right? But it's usually very specific shape of a receptor, specific thing it attaches to, neurotransmitter in this regard. Enzymatic proteins. These guys carry out metabolic reactions. We will see these a lot in when we talk about metabolism. Okay, we talk about cellular respiration. We have a number of metabolic reactions that are driven on that plasma membrane by various enzymatic proteins. Okay, where they're going to, attach a phosphate to ADP to make ATP. Okay. There's a number of other ones as well. Okay. That cause a cascade of events inside of a cell. The last one, and just because it's last doesn't mean it's the least important one, it's probably one of the more important ones, to be honest, is junction proteins. Having an individual cell is awesome and fantastic. I need cells to stick together so I can make tissues. I need tissues so I can have organs. I need organs so I can have an organ system and I can be me, right? Because without cells sticking together, okay? So without cells sticking together, who the hell cares, right? Doesn't matter. I need cells to stick together to get more complex structures, tissues, okay? To get more emerging properties, all right? And it's the ability for all these various different cells to stick together that allow us tissues and organ systems and the organism itself, okay? Very important, those junction proteins. And there's a number of those, and I believe we'll talk about those at the end when we talk about some extracellular specializations, okay? We'll highlight some of those and show you why they are important. There you go, pictures with words to prove I'm not a liar. There you go. All right, so let's get into some of this stuff here, all right? How does this do? Okay, this is just kind of what I talked about here. Here's the example. And I apologize for how this looks. It looks like the lines are on top of each other, and I honestly, I've changed the font, I've changed the spacing between this stuff, and it just, for the life of me, I cannot fix this slide and how it appears and looks. So I apologize for that, because this kind of annoys me. All right. Again, we have specific signaling molecules. Okay. We have specific receptors. Okay. Once they dock, I get a cascade of events, and that's what this picture is trying to show you here. Here's a signaling molecule. It has a specific shape. Okay. It has, here's my receptor protein. Okay. It has a specific shape, a specific shape. So when this molecule docks to it, then it causes a, what's called a cascade of events, okay? And it can make proteins, and it can make all sorts of fabulous things, okay? This secondary messenger system that we're ultimately creating with the signal protein allows it to alter the shape of the cell, alters its metabolism, alters the way that it makes things inside. So I can get a specific response with a specific shaped molecule, specific shaped receptor, and I get a specific outcome in the cell. Okay. So these receptors are very specific. I keep saying specific and specific and specific because it is, all right? This could be a signaling protein to, this could be a signaling molecule to make a protein. This could be a signaling molecule to create ATP. This could be a signaling molecule that causes a change in structure, and all of a sudden you start to get this thing start to fold in on itself like this and make a neural tube, and then you get specialization, and it causes this top part here to create this bulbous structure, the brain. Okay. You get a signaling protein that happens at a certain time during in utero development, and all of a sudden a little arm bud pops off here. Okay. You get another signaling protein, and it eats away at the skin in between the fingers, and you get individual fingers. So these signaling proteins are very specific. It's a very specific cellular response, and it could be anything. That's what I'm trying to get across here, okay?